So, in my recent absence, I've received a request. Right when I was thinking about returning from the void, because the building work going on underneath and around me is pretty much finished by now, and it's a bit less annoying. Anyway, let's read what I've been asked. Hi Alan, I'm a huge fan, love your videos, and that audio chocolate that is your voice. I bow down to your extreme intellect, and I humbly ask for a favour, as I have been having a few problems with my new A-level physics work on particles. I was hoping you could return from your wilderness and see what you can do, because you are incredible. Thanks. Well, thank you for the request. I'm not going to name and shame. You know, people who express that kind of love for people, they deserve to keep it behind closed doors. But they were kind enough actually to send me a few of the questions from their A-level questions that I've kind of based this around. I've not directly answered anything. I've tried to address all the points that could come up in it, and I've rewritten a couple of the questions to ask them later on so we can work through them as examples. If I just told you the answers, how would you ever learn? Anyway, let's quickly move on into looking through what I've prepared. And first off, you'll see that I've talked about atoms. You know, we used to think of them as indivisible. They actually come from the Greek for a, not, and tem, nine, to cut, atomos, then became atom in French, and then it's into the modern day. And as you can see here that I've stolen from dictionary.com, it does actually acknowledge that it gets broken down into even smaller particles, like quarks and leptons and force carriers. For example, quarks and leptons will just stick at the simpler end of that. That's the ups, downs, and electrons and neutrinos. I'm not going to go through charmed, strange top and bottom because they just sound weird. You can also see here that we've got antimatter to consider. You've got electrons and their counterparts, positrons, protons and their counterparts, antiprotons, neutrons and their counterparts, antineutrons, and neutrinos and antineutrinos, just like there. And if we carry on going down this rabbit hole, we eventually get down to the idea of string theory, where it may be that energy just coalesces into matter at a certain point. But So it's important though to understand that with the antimatter being there, this will react with matter in a certain way. If you've ever read Angels and Demons by Dan Brown, watched any sci-fi shows, or watched Scott Manley's Kerbal Space Program mod series, Interstellar Quest, which I've been rewatching recently, it's a lot of fun but very, very long. Be prepared to have a time investment if you want to watch it, and an interest in astrophysics. It's a very, very good series. It doesn't handle anything head on, he explains it as he goes along. I'd definitely give it a watch, and I'll try linking the playlist down below. Anyway, we mentioned annihilation. It's not just a song by a perfect circle. It is the process that happens when matter meets antimatter. As you can see here, you kind of got an electron and a positron pinging off, and they can release gamma ray photons, for example. It's also a film based on a novel by Jeff Vandermeer. Not really sure what's going on about it, but I know that the cast is mainly playing scientists. Anyway, as I mentioned, when things collide, you don't just get rid of them. There has to be something that comes about, and that's energy. We can look though at pretty much an opposite of pair production. This is kind of when, rather than taking an electron and a positron, the anti-electron, and getting rid of them to produce a photon, well, two photons actually, we'll cover that later. This is where you take a photon and then that goes away and the energy becomes matter. It becomes an electron and a positron, a proton and an antiproton, for example, potentially. So it's a counterpart to annihilation. You need a photon though of enough energy to overcome the rest masses at the very least of what's going to be produced. You need the rest masses to be covered for as well as any kinetic energy. So this is like this here, basically. So annihilation though can get quite complicated. I only really mentioned it so far with regards to the smaller particles, that being individual quarks or individual leptons. But we can see here though that you've got protons and antiprotons. These are made up of quarks. Each of them contains three valence quarks within. There's usually as well known to be a sea of quarks bobbing about this. What actually happens though on this level is that because you've got the three valence quarks, two of them can annihilate with each other first. And you see here that you've got different colours. The yellow and the blue quarks kind of are the exact opposites rather than the counterparts within the same one. So they share the same charge, well, opposite charges. They're the exact opposites to one another. So they will annihilate with each other, producing a gluon, which then goes on with the other valence quarks to continue this reaction down until eventually you get emitted electrons, positrons, gamma rays, neutrinos, and just a lot of energy given off. This reaction can keep on going throughout each of these quarks until you've got rid of the entire proton and the antiproton. That will give a lot of energy, as we saw before. As we mentioned though, everything has energy. could be considered that everything is made of energy rather than matter. Matter may not exist and everything is energy, but I'm not going to go down that rabbit hole again, otherwise Luke will look disappointed at me again. But E equals mc squared, the old Einstein equation, energy is equal to mass multiplied by the speed of light squared, and it actually applies to all this stuff. We've actually quoted the masses of electrons, positrons, protons, antiprotons, antineutrons, neutrons, neutrinos, and antineutrinos in energy, in mega electron volts being a million electron volt being a tiny little fraction of a joule. It's impractical to consider it in joules. We use electron volts for these things as non-SI units because things are so small and virtually irrelevant. But anyway, you can see that with pair production, the kinetic energy of that photon that comes in is going to have to exceed the combined rest masses of the electron and the positron. So it's going to need to be greater than approximately 1.2 mega electron volts. For protons and antiprotons to be formed, you're going to have massive, nearly 2,000 mega electron volts. Colossal energies compared. However, if you're working backwards and you're annihilating, you annihilate a proton and an antiproton, even at their rest masses, that's going to be a lot of energy given off. Getting on again for 2,000 mega electron volts for the two photons being given off. So you'll be getting 938.257 mega electron volts per photon emitted. You get two photons emitted as well to make sure that momentum is conserved. Momentum must always be conserved. It's not just momentum that needs to be conserved as well, it's quark numbers, lepton numbers, angular momentum, and electric charge. So we're going to go work through an example. I've rewritten the questions from the A-level questions sent to me. So we're going to take here a proton. Its rest mass 938.257. Its kinetic energy. Here we've decided it's going to be 1 mega electron volt. So fairly low energy, but you get 939.257 mega electron volts as the combined energy of that proton, the overall energy of the proton going into the annihilation. I'm going to take the antiproton. That's going to be knocking around, say, at absolute zero. The only way you can get it technically without any kinetic energy. So it's actually going to have 938.257 mega electron volts available as energy, just its rest mass. Total energy of the system, so that's going to be for the two photons released, is going to be the combined energy of the two annihilated particles. So it's going to total up to 1877.514. Because there's two of them, they're going to have an average of 938.757 mega electron volts per photon. But remember that you conserve the momentum, so one might be moving different vectors, for example, as well. It hurts my head thinking too much about that one. But then we'll have a look at pair production. We'll work backwards on this. We'll go for the annihilation, then we'll look at the pair production. And here we'll take the photon of energy, 3 mega electron volts. You can tell this is a much lower number than 938.757 that we were getting from that previous annihilation. Even taking out the energy as well, it's way lower than 938.257 mega electron volts that a single proton would need. So rest mass of a proton is 938.257, neutrons even higher. We're not going to be getting any protons and neutrons formed from this pair production. Especially not when you have to consider that you've got to make two of them to balance out the quark and lepton numbers and the charge, for example. So therefore, we're going to be getting half of the 3 mega electron volts. It's 1.5 MeV from a photon. It's going to be produced in the pair. So the rest masses of electrons and positrons, though, actually come in at 0.510999 mega electron volts each. So we've budgeted 1.5 mega electron volts for each of the pair. This greatly exceeds the 0.5100999 mega electron volts of the electron to be produced and of the positron to be produced. So we actually exceed the threshold by nearly 1 mega electron volt. Therefore, we've got a nice amount of kinetic energy, and that's going to fire around. You get fast moving things emitted. But finishing off with positron emission, this one gets a little bit complicated at times as well. It's when a proton becomes a neutron. This is usually because of an imbalance in the nuclear structure. So whether it's because you have too many protons, for example, it causes instability. Here we look at 23 magnesium going to 23 sodium. 23 magnesium is usually 24. So that's why it's become sodium, because of the imbalance. And then you kicked off a positron and an electron neutrino. So basically what has happened here is that your atomic number has decreased by 1. I will be doing a video eventually talking about the periodic table and isotopes. It'll be quite fun, I hope. But anyway, this is mediated by the weak nuclear force, one of the 4 fundamental forces. You've got the weak nuclear force, the strong nuclear force, the electromagnetism, and gravity. Gravity is the weakest, but it has by far the biggest range, which is why we feel gravity from all across the universe. It's basically unlimited range. The strong nuclear force mercifully has a very short range, otherwise everything would just be a singularity, because it's incredibly strong. As soon as you touch something, you'll become part of it and could never separate off. Anyway, there's also a counterpart to positron emission where you actually get electron emission, where a neutron changes into a proton, and then you get an anti-neutrino. But if we look here, we've got up quarks, down quarks, electrons, and electron neutrinos. These are what we want to look into. And we'll look at the poorly drawn proton from earlier on. We'll work through how this all happens. So we know it happens. We know kind of why it happens. Now for the how. Every proton and neutron is composed of quarks. To keep things simple, we'll just consider the up and down. We won't have any flavors in these. So you've got two ups and a down. Up is 2/3 plus 2/3 charge. Down is minus 1/3. So therefore, to get a proton, we've got two ups. So that's 4/3 minus 1/3 is a net charge of +1. So we're going to have to conserve the net charge of +1 as we go through this whole situation. So what we actually get is one of these up quarks converting into a down quark. And I've also noted that it's gone down to join its friend there. But that means that we've actually gone from 4/3 minus 1/3 to 2/3 minus 1/3 minus 1/3. So we've got no net charge. This cannot work. So we've seen that it's flipped. This can't be the end of the story. We get a positron, so beta plus rather than beta minus, which would be an electron, and a neutrino coming off to balance the books. Your net charge is back to +1. Just for clarity as well, I'm not really going to go into it. There's a process known as electron capture. Here an electron is actually absorbed by the nucleus, which then turns into a proton, into a neutron rather, and kicks out a neutrino. Tends to occur in low energy situations as it does not involve the production of a positron, but actually the death of an electron. Anyway, I hope that this has been fairly interesting at the very least, and also fairly helpful. I'm gonna go now before I carry on thinking down this line too much and make my brain start to ooze out of my ears. Let me just do some more chemistry next time because I actually know that off by heart rather than having to go and learn all this on a Monday morning to make a video on request. But anyway, I've kept things fairly simple. Thank you to the InspiroBot generator here for the fantastic, inspirational, remember to rethink everything. But for now, everyone, all I have left to say is, well, you should know it by now. Laters.